Hi students, welcome to Max Point of View. Today we are going to learn the concept of radioactivity part B, that is nuclear fusion and fission reactions. So in this chapter, after learning this concept, we are going to solve each and every theory question. That video will also be available in the description box. So without wasting any time, we'll start with our concept. Before jumping into the nuclear fusion and fission reaction, we need to understand some basics. First, what do you mean by nuclear energy? The energy released by the nucleus during the nuclear reaction. During the nuclear reaction, the energy released by the nucleus is called nuclear energy. And there is a concept of loss of mass. This concept is very much important. Why? Because many give reason questions will be based on this one only. Okay, what do you mean by that? That means whatever the reactants we are going to use, that is nothing but whatever the if you take one equation, whatever the reactants, okay, before the reaction, those are called reactants. After the product, once they form the product, there will be a loss of mass. There will be a loss of mass. Because of the loss of mass only, huge energy will be created. Keep this in mind. So in the question, they are going to ask you why huge energy is released between nuclear fission or nuclear fusion reaction. Why? Because there is a loss of mass of the substance on the product side. On the product side, that results in release of huge energy. Keep that in mind. That is what we are going to learn here. Now next, for this one, how much energy is released, all those things, for that one, theory of relativity was given by Einstein. Using this theory of relativity only, we are going to find the answers, how much energy is released, all those things. What do you mean by theory of relativity? There will be exchange of mass in terms of energy. How much mass is lost, that much energy will be released. This is nothing but theory of relativity. Using this concept only, Einstein explained one equation, that is nothing but E is equal to delta m c square. Delta m represents, actually there is no delta, that means mass. Delta m represents loss of mass. I told you there will be a loss of mass, correct? On the product side, after the reaction, there will be a loss of mass. That is nothing but how much mass is lost into c square. What is this c? Speed of light in vacuum. That is nothing but 3 into 10 power 8 square. 3 into 10 power 8 square. So this, using this equation, we can aramse find how much energy is released, that too in the form of joules. That too in the form of joules. Energy will be in the form of joules. Next, how in 1 kg of mass, if the 1 kg of mass is lost, then 9 into 10 power 16 joules energy is released. 9 into 10 power 16 joules of energy is released. If this value is converted into kilowatt hour, this we have learnt in electricity chapter itself, right? How we can convert joules into kilowatt hour. So that will be 2.5 into 10 power 10 kilowatt hour. So if they are asking the answer in terms of joules, this will be your answer. If they are asking answer in terms of kilowatt hour, don't need to convert it, just by heart this value, you can aramse write it. So what do you mean by this one? If 1 kg of mass is lost, 1 kg of mass is lost of a substance, this much energy will be released. 9 into 10 power 16 joules of energy. If you want to convert this energy in form of kilowatt hour, this is the value. And there is one more concept, AMU, atomic mass unit. That means instead of giving the values in terms of kg, we can also write AMU. Okay, atomic mass of a particle. Next, one atomic mass unit is equal to 931 mega electron volt. When you see this one, mega electron volt, mega means 10 power 6, electron volt is another unit of joule, So in this chapter we are going to talk about mainly this mega electron volt. Joule and kilowatt hour will rarely talk about them. Mainly we are going to talk about mega electron volt. So whenever you see mega means 10 power 6, okay, electron volt, this electron volt is another unit of joules. So don't worry about these two that much. This is very much important because most of the reactions, after they releases energy, we are going to represent in terms of mega electron volt only. So don't get confused, it is one form of energy. The unit, this is one unit of energy. That's it. Now we learn about nuclear fission. See, what do you mean by nuclear fission? First I'll define it, then I'll explain it. Listen, nuclear fission is a nuclear process in which a heavy nucleus splits into two lighter daughter nuclei of nearly the same size, with the release of tremendous amount of energy. When it is bombarded with slow moving neutrons, it releases tremendous amount of energy. So this is the definition. That means a heavy nuclei splits into two daughter nuclei of lighter. These two will be lighter. So when this will be released, when it is bombarded, when the heavy nucleus is bombarded with the slow moving neutron, these two daughter lighter nuclei will be formed. Along with the daughter nuclei, tremendous amount of energy will be released. Listen, that is the definition of nuclear fission. Energy will released, we got to know how much energy will be released. That is 190 mega electron volt. This is a very huge amount of energy is released. Okay, when it compares to fission reaction and fusion reaction, fission reaction releases more required energy. So fission reaction produces more energy than the fusion reaction. We did not learn anything about fusion, right? We are going to learn, so just remember this. Next, why huge amount of energy is released? This is what we have learnt in basics, correct? That is nothing but in the previous slide. So the amount of energy released because of the loss of mass. We understood, right? That is nothing but, that is how the Einstein explained it. Theory of relativity. That is nothing but how much mass is lost, that much energy will be released. More the mass is lost, more the energy will be released. So why the energy released, why the huge amount of energy is released? These kind of questions are going to ask in theory questions. So the answer will be the loss of mass of a substance on the product side. On the product side is the main cause of huge energy is released. Next, so this is one example. There are many examples. This is one example. This one example is enough to write it in the exam. So whenever they are asking about nuclear fission or fusion, just remember only one example. By heart it, only one example. Whatever the example they will ask you, write that only. For nuclear fission, you always write this one, or you can choose anyone in the textbook, anyone from the textbook. Now listen. So listen, 235, this uranium is the substance. That is what we are going to bombard with slow moving neutron. Whenever these two are bombarded, this forms a uranium that will be split into two fragments. These are called two fragments. Along with this one, 3 neutrons will be produced. Along with this one, E represents energy. Huge amount of energy. How much is that? 190 mega electron volt. Okay, now listen. So if you by heart it, and sometimes in the exam they may ask you, they'll give you the unfinished the equation. You have to complete with the numbers. That is very easy. That is what we have going to learn in the theory solution. I'll teach you here. The one important thing about is atomic mass number. Okay, A is nothing but mass number or atomic mass number, both are same. Mass number and the atomic number, are conserved. This is the hint to complete the equation. That means, see, first we'll talk about mass number. How much is the mass number here? 235 plus 1. The above parts are mass number, correct? 235 plus 1, that is 236. So in this equation, totally what is the mass number? 236. So they'll give you this one or this one. Assume 144 is given, and we have to write the value here. And there is one more hint here. So 144 is given. We don't know this value. 144 plus x plus what is this value? If just one neutron 10 is there, only 1 is the mass number. But here 3 neutron is given. So 144 plus x plus 3 into 1, that will become 3. That should be equal to 236. So you can aramse find the x value, correct? This is how we are going to find this value. If this value is given, same method only. Okay. neutron, see here you should not get confused. If 3 is not there, 1 n 0 is given, then the mass number will be just 1. Okay, mass number, we have to add whatever the mass numbers we have here. If you add all these things, the complete mass number we have at the reactant side will be equal, both will be equal. That is why it is said to be, but the mass number and atomic numbers are conserved. That means in atomic number also, what is the atomic number? 92 plus 0, it is 92. Here also, see the atomic numbers below part, 56 plus 36 plus 0, 3 into 0 will become 0. So we are going to add these two only. 36 plus 56 will give us 92. That means on the reactant side, this is called reactant side, and that is called product side. So on the reactant side, the whatever the mass number is there and the atomic number is there, that will be equal to the sum of atomic numbers and mass numbers. Both will be equal. That is why atomic number and mass numbers are conserved. But what is the problem here? Atomic number and mass numbers are conserved, but not the mass. Mass will be reduced. See, whatever the mass we have on the reactant side, that will not be equal to the product side. Mass will be lost. Some mass will be lost. Whatever the mass is lost, that is why we are getting huge amount of energy. So in the theory solution, if I am using E means energy. You got my point? E means energy. Because of the loss in mass, we are getting the energy. But atomic number and mass number, whenever you add it, okay, if you solve it, you will get to know. That is what we are going to do in theory solution. Don't worry about it. Atomic number and mass numbers are conserved. That means both the side it will be equal. Next, two fragments are unstable. What do you mean by two fragments? I used it one time. Two fragment means on the product side, whatever the fragments we are getting, whatever the different elements we are getting, barium and krypton, both are the different fragments, different elements, right? Those are called two fragments. These two produced fragments are unstable. These two are unstable. So what they'll do is they release beta and gamma radiation, to become stable. So this question they may ask you, the fragments released in nuclear fissions are unstable, how can they become stable? Very simple answer, they release beta and gamma radiations to become stable. So these are some basics about nuclear fission. So we'll learn some more facts. After that we can jump into controlled and uncontrolled chain reaction. Now we learn some facts about nuclear fission. Listen, 1 gram of uranium 235-92 releases 4.8 into 10 power 23 mega electron volts. Just 1 gram of uranium produces this much of a amount of energy, and that will be equal to, how can we compare it? Have you heard about TNT bombs? 20 tons of TNT bomb, how much energy will be released? That is equal to 1 gram of uranium 235-92. So whatever this uranium releases energy, that will be equal to 20 tons of this TNT bombs. How much this releases, that will be equal to just 1 gram of uranium. That is why this one nuclear fissions are very dangerous. Okay, we are going to learn one more fact. Listen, based on these two they may ask you any question. Listen, now uranium 235-92, this question is there in the theory question. That's why you have to learn it properly here. There are two isotopes. These are two isotopes, uranium isotopes, 235-92, 238-92. Okay, now what will be the question? Out of which is easily fissionable? The answer is uranium 235-92. Why? What do you mean by easily fissionable? That means it does not demand so many things. I'll give you one example. Uranium 235-92 is fissionable even by slow neutrons. Slow moving neutrons are enough to fission the uranium 235-92. That is why it is easily fissionable. But what about uranium 238-92? It requires only fast neutrons. neutrons. That's why it is not easily fissionable. So what is the answer? Out of these two isotopes, which is easily fissionable? 23592. Why? Because it is fissionable even by the slow neutrons. Even by the slow neutrons, it is also possible with fast neutrons. By the slow neutrons only it is possible, but when it comes to uranium 23892, it is only fissionable. It is only fissionable by the fast neutrons. By the fast neutrons. This is the reason why uranium 23592 is easily fissionable compared to uranium 23892. Now we will talk about controlled and uncontrolled chain reaction. So before understanding that, we need to understand what is chain reaction. Listen, this is an example equation we have taken for nuclear fission. So nuclear fission is also called as controlled chain reaction or uncontrolled chain reaction or chain reaction. So first we need to understand all those things one by one. Before that, we will first understand chain reaction. So this is the equation we have taken, correct? So in this one, see, these two are the fragments. These two are the fragments are released because of the uranium. Along with this one, 3 neutrons are released. New neutrons are released. When these neutrons are released, new neutrons are released, this will, see, we know some part of the mass will be lost, correct? This we have learnt earlier. Some part of the uranium will be lost. Whatever the uranium is left, these newly produced neutrons again, okay, combine with the uranium to form new reaction, that is nothing but chain reaction. Now we understood the newly formed neutrons, okay, in the product side will again combine with the uranium, okay, to form fission reaction again and again until the complete mass of uranium is consumed. So here I am taking the concept substance as uranium. If you are talking generally, then you can talk like the newly produced neutrons will combine with the substance, and so it forms a fission reaction again and again until the complete mass of the substance is consumed. The complete mass of the substance is consumed. That is nothing but chain reaction. So during the chain reaction, you know, so whenever one reaction is done, energy will be released. So continuously, this is called as chain reaction. It keeps on reacting. So whenever the reaction is happening, the energy will be keep on increasing continuously. So it will be released continuously. This tremendous amount of energy is very harmful, and it can produce a strong explosion with a very short interval of time. Okay, in a very short interval of time, it can produce strong explosion. That is why it is called as uncontrolled chain reaction. Now you got my point. What is chain reaction? Because of the newly produced neutrons, it will interact with the uranium to start the fission again, okay, in a chain. Okay, it will keep on creating the fission reaction until the complete mass is consumed. That is chain reaction. Why it is called as uncontrolled? Because whenever the chain reaction is happening, energy will keep on increasing. Energy will be keep on increasing, and this energy is strong. We can produce strong explosion in a very short interval of time. That is very harmful to us. That is why it is called as uncontrolled chain reaction. Now we'll talk about controlled chain reaction. How we can control it? Whenever this is happening in the nuclear reactor, in the nuclear power plant, whenever the nuclear fission is happening, so we'll use two materials so that it can be aram se controlled. We use two different materials like cadmium rods and moderators. Okay, what is the function of cadmium rods? These cadmium rods absorbs the newly produced neutrons. Absorbs the produced neutrons. Only few. Absorbs some of the produced neutrons, not all, only some. These moderators will slow down the neutrons. So cadmium rods absorb some of the produce neutrons, and remaining neutrons will be slowed down by the moderators. In the moderators we are using graphite or heavy water, etc. Anything can be used, any one can be used as a moderator to slow down the neutrons. So hence we are slowing down and absorbing some of the produced neutrons. This chain reaction can be controlled. This is nothing but controlled chain reaction without using cadmium rods and moderators. That is nothing but uncontrolled chain reactions. So whatever the energy is produced here, okay, anyhow the fission reaction happens, right? So whatever the energy is produced here, it is used for constructive purpose. What do you mean by constructive purpose? That is nothing but producing electricity. That is the principle of nuclear reactor. What is the principle of nuclear reactor? The energy produced in the fission reaction, okay, should be used for constructive purpose. That is the principle of nuclear reactor. Now we'll talk about the uses of nuclear fission, only fission. So first one, destructive purpose. We already know destructive purpose means destroying something. So here for a destructive purpose we use it as nuclear bombs. Nuclear bombs. So sometimes it is also called as atom bomb. Atom bomb. The word atom bomb is a misnomer. What do you mean by misnomer? Misnomer is nothing but it's an inaccurate word. So if you are using atom bomb, the word atom bomb is a misnomer. That means the atom bomb, the word atom bomb is an inaccurate word to describe it. The actual name, so we should use it nuclear bombs. Misnomer is nothing but inaccurate word to describe the name. That's it. Now in this nuclear bomb, it is uncontrolled. It is uncontrolled. See, what do you mean by uncontrolled? In uncontrolled chain reaction, huge energy will be released. During the huge energy releases, it can produce a strong explosion in a very short interval of time. We want that explosion for destructive purpose, right? That is why uncontrolled chain reaction is used. Uncontrolled chain reaction. This is based on destructive purpose. For destructive purpose it is based on uncontrolled chain reaction, okay, which releases huge amount of energy, okay. That energy will cause the explosion. Next, for constructive purpose. See, for constructive purpose, to produce electricity. To produce electricity. This is the purpose. This is the principle of nuclear reactor. What is that? Whatever the energy is released, that should be used for constructive purpose. That is the principle of nuclear reactor. So for a constructive purpose we produce electricity. That will be controlled chain reaction. Controlled chain reaction. We understood what is controlled chain reaction in the previous slide, right? Now so why we are using controlled chain reaction? Here even though energy produced is less compared to uncontrolled chain reaction, here there will be no explosion. There will be no explosion. So here we are using controlled chain reaction. Energy released will be less than uncontrolled chain reactions. So these are the uses of nuclear fission. So now we learn about the difference between radio decay, radioactivity and nuclear fission. Radioactivity in also we are releasing some radiations. In nuclear fission also radiations will be released. That's why we are comparing them. And this comparison, whenever we receive in theory questions, we are not going to solve there. We are solving here. We are learning in depth here, right? So that's why the same question, if they ask in theory solution, whatever we are going to solve in the upcoming video, that is already present in the description box. In that, if you get these kind of questions, the differences, the same questions and all, we are going to skip it. That's why you learn it here better. Okay, listen. Radio decay or radioactivity, okay, it is a spontaneous process. It is a spontaneous process. This is non-spontaneous process. What do you mean by spontaneous process? So it occurs by its own. Okay, without any initiation, it will start by its own. That is nothing but spontaneous process. Here, nuclear fission is a non-spontaneous process. Okay, or else you can write it as it will not occur itself by themselves. Next, energy released is less compared to nuclear fission. Here, tremendous amount of energy will be released. Okay, so here energy produced will be less, there tremendous amount of energy will be produced. Then rate of decay cannot be controlled. Here rate of reaction or rate of nuclear reaction can be controlled. So these are the differences between radioactivity and nuclear fission. Why we are comparing? Because in both the this process they are producing radiations which are harmful to human beings. Now we learn about nuclear fusion. First I'll explain the definition. So nuclear fusion is a process when two lighter nuclei combines together to form a heavy nucleus, which releases huge amount of energy. This is nothing but fusion. Two nuclei to form one heavy nuclei, two lighter nuclei to form one heavy nuclei. But nuclear fission, heavy nuclei will split into two lighter nuclei. That is nuclear fission. Here two lighter nuclei combines to form a heavy nucleus. That is nuclear fission. Here also energy will be released. That energy released will not be equal to the nuclear fission energy. Nuclear fission energy is very huge. Okay, it will be in terms of 190 mega electron volt. Here it will be less than 50 megavolts only always. Next, so we learned the definition. This is one example. You can by heart this example. Okay, sometimes they may ask you to identify which kind of equation is this, whether it is nuclear fission or nuclear fusion. Very simple to identify. In nuclear fusion, the numbers will not exceed more than 10. The numbers will not exceed, the above or below numbers will not exceed more than 10. That means, and there is one more way to identify. In nuclear fission, the numbers will be higher. It will be more than 230, all those things, and uranium is the substance. Here hydrogen or heliums are the substances. There are two ways to identify. One with the numbers will not cross more than 10 in nuclear fusion, but in nuclear fission the upper or below numbers will be more than 10, and it starts from uranium, and here it starts from hydrogen or this one helium. Now the one equation you can by heart. How to complete these equations we are going to learn it in theory solution. Don't worry about it. Next we'll talk about temperature and pressure. This one, nuclear fusion will not occur at ordinary temperature and pressure. Keep this in mind. Will not occur at ordinary temperature and pressure. But nuclear fission reaction will occur at ordinary temperature. Why it is not possible? Why? Because see, what do you mean by nuclear fusion? We are combining two nuclei. So in the nuclei, what are the constituents? Proton and neutron. Neutrons are negatively no charge, correct? Neutrons are no charge, but protons are positively charged. In both the nuclei, we have protons are positively charged. Whenever you are trying to combine two positively charged particles, do you think that will happen? No, because the electrostatic force of repulsion. Why repulsion? Because both are positive. If both are negative, also repulsion will be there. When will be there the attraction? When the one is positive, one is negative. But here both the nuclei has only protons. That's why positive and positive will repel. That is called as electrostatic force of repulsion will be stronger. So that's why along with the in the ordinary temperature and pressure it is not possible. So what we have to do, we have to create a huge temperature and pressure. It will happen at a high temperature and pressure. These two neutrons, okay, will fuse, combine to form a energy. So what temperature we required? 10 power 7 Kelvin temperature. About the pressure, don't worry about it. The amount of pressure is not mentioned in the textbook. Only this much you should know. 10 power 7 Kelvin amount of temperature is required to melt, to combine those two nuclei. Then what is the another name for nuclear fusion? Very simple. Anyhow, it is using a high temperature. Okay, it is called as thermonuclear reaction. Why it is called as thermonuclear reaction? Because it occurs at very high temperature and pressure. That's why it is called as thermonuclear reactions. So this is the definition, example, and this is the condition. Only nuclear fusion requires high temperature and pressure, but nuclear fission, okay, can occur at ordinary temperature. Another name for nuclear fusion is thermonuclear reaction. Why? Because it occurs at only high temperature and high pressure. Now we'll learn some facts about nuclear fusion. See, sun and star. Inside a sun and star, the huge amount of energy will be released because of nuclear fusion. Keep this in mind. Nuclear fusion. So how this energy will be released? 4 hydrogen nuclei form. What do you mean by nuclear fusion? Combining the 2 lighter nuclei, but here 4 hydrogen nuclei will combine to produce helium. So whenever this is producing helium, the huge amount of energy will be released. This is not the exact equation, just to make you understand. So 4 hydrogen nuclei will combine to form helium along with the energy. This is what happens inside a sun and star. So that's why it is called as nuclear fusion. Why it is called as nuclear fusion here? Because many lighter nuclei are combining to form a heavy nuclei. These are lighter and this is a heavy. That's why it is called as nuclear fusion. Okay, next, hydrogen bomb. Okay, in both sun and star nuclear fusion and hydrogen bomb, in both the process the temperature required will be 10 power 7 K. Keep this in mind. In both the cases it is 10 power 7 Kelvin. Okay, temperature is required, okay, to get that energy what is required and to get combined. For combining the nuclei we require 10 power 7 Kelvin. We have learnt why, correct? Now in a hydrogen bomb, this hydrogen bombs also works on the principle of nuclear fusion. Atom bomb or nuclear bomb works on the principle of nuclear fission. Atom or nuclear bomb. Hydrogen bombs works on the principle of nuclear fusion and requires 10 power 7 Kelvin of temperature. Next, energy produced per unit mass. Very important. We know in nuclear fission, after the fission reaction, the huge amount of energy is released compared to nuclear fusion. Which is in which reaction energy will be more? Nuclear fission. But when it comes to per unit mass, how much mass is lost? When you compare the amount of mass is lost and the energy in nuclear fusion, energy will be greater than fission energy. This is very much important. So in which reaction more energy will be released? Fission reaction, nuclear fission reaction. But energy produced per unit mass, for some mass, okay, for the same amount of masses in both the reactions, the energy released in nuclear fusion will be more. That's why nuclear fusion energy is greater in than the nuclear fission energy when it comes to per unit mass. If you see this word per unit mass, in which nuclear reaction per unit mass energy is more, that is nuclear fusion. Without this word per unit mass, in nuclear fission only energy will be more compared to nuclear fusion. Without this word, fission is greater. With per unit mass, fusion energy is greater. That's it. Next, difficulty. What is the main difficulty about nuclear fusion? That is attaining this 10 power 7 Kelvin of temperature is very difficult. That is the main difficulty of this nuclear fusion. These are the facts, and we have learnt everything about nuclear fusion. Now we are going to learn the differences between nuclear fission and nuclear fusion. That will be our last concept. Now we learn the differences between nuclear fission and fusion. We have learnt it in properly, but here we are going to learn the differences. Listen. First, whenever they are asking for the definition, and whenever keep one thing in mind, whenever we are going to talk about the differences in theory solution, we are going to skip it, because in the concept video here we are learning in depth. In the theory solution they will ask for 2 or 3 differences. We are learning everything here. You can choose any 2. Listen, nuclear fission and nuclear fusion. First, write the definition. Always go for the definition. Next, nuclear fission occurs at ordinary temperature and pressure, but nuclear fusion requires 10 power 7 Kelvin temperature and high pressure. Don't worry about the value of pressure. Okay, so nuclear fission occurs at ordinary temperature and pressure, that requires 10 power 7 Kelvin, and here energy released by one reaction is 190 mega electron volt. Energy released by just one reaction is 190 mega electron volt. Here it is the complete energy produced by one complete reaction is 24.6 mega electron volt. This is the maximum. Next, per unit mass. But when you take per unit mass energy released is less compared to fusion. In fusion reaction, per unit mass, for the same amount of mass in both reaction and fusion, okay, fission and fusion, for the same amount of mass in fusion reaction, the energy released in the fusion reaction energy released will be more compared to this one, fission reaction, for the same amount mass. But here the masses are different, that's why we are getting huge amount of energy. But for the same amount of mass, the energy released by the nuclear fusion will be more compared to the nuclear fission. Why? Because here in the normal reaction the amount of mass we are using is more. Okay, that's why we are getting huge amount of energy. Then fissionable substances are less limited. They are limited. Fissionable, to find the fissionable substance, they are very limited. But for this one, fusionable substances are abundance. Okay, they are occurring in abundance form. Then nuclear fission reactions can be controlled. This can be controlled. Nuclear fusion cannot be controlled. Then the final one, this, okay, based on the nuclear fission, atom bombs are produced. Based on the nuclear fission, atom bombs. Based on the nuclear fusion, hydrogen bombs are produced. These are the differences. Then what is the similarity between these two reactions? Now we have understood the complete concept of radioactivity part B, nuclear fusion and fission. After this chapter, immediately go for the theory solution, and we have only 2 numericals that will also be done along with the theory solution in the same video. So that video link will be available in the description box. After solving the videos of all the chapters like this, we are going to solve the question papers, okay, previous year question paper from 2017 to till year, that is 2024, okay, that to chapter wise. So in radioactivity chapter, okay, you can take any chapter. In a light chapter, what are the questions they have asked in 2017 to 24, so that you will get to know in only one chapter what are the questions you can expect. I am not going to solve each and every paper, okay, we are going to solve the papers in a chapter wise, so that it will be definitely useful for you to understand, and you can expect the questions in the board exam. After that, after this one, from 2025 onwards, whatever the paper we are going to get, that we can solve it directly. Thank you.